All right, good morning, y'all. I hope y'all are having a good day. My name is Catherine San Gabriel, and I will be talking about heat gains and heat loss calculations. I did the best I could with this. I wasn't exactly sure how to put this all together, but I just hope that y'all will learn something from it. And let's get right into it. So to begin with, I just want to talk about heat flow and insulation. So to get started, heat flow flows down like water, which means it just goes from hot temperatures to low temperatures. And usually temperature is what drives heat flow and is measured in BTUH. And insulation plays a big role in heat flow since it helps slows down heat flow, but it doesn't necessarily stop it. And a lot of the buildings use internal air spaces to limit the conduct of heat flow. And a few examples that the type of installations that are used inside buildings would be fiberglass and mineral wool. And insulation is pretty big whenever it comes to finding being able to conserve heat and heat flow. The next thing is, how do we calculate heat gain and heat loss? Well, it all really starts by knowing the four factors of heat calculations, which is R values, U values, infiltration, and ventilation. And I know in the previous presentations they've talked about R values and U values, so I'll try not to get too in depth with them either. But for U values are the reciprocal of R values, and they refer to conducting heat in construction and defined in BTU. And the formula for it is U equals, B2H times 1 square foot and times one temperature difference. And then that's how you really calculate it. The next one is R values. And I gave a little sheet to kind of give an example of the R values, materials, and like how resistant they are to heat flow. Usually the higher the value, the better resistance the material has against heat flow. And they use their R values are used to find the heat flow in construction, and depending on the material that they use, it really helps to find out the answer. So an example would be like if you're making walls out of stucco and brick, then you simply add both the materials together, and that'll help you find the heat flow through the wall. And usually finding the R values are important because once you find the temperature within the wall, you'll be able to find the internal temperature. The internal temperature is also important because it'll help you find a good place to put the vapor barrier inside the building. Because if you don't find a very good place for it, then sometimes the temperature will make people discomfort. They won't find comfort in the temperature. Like there'll be one that's too hot, too cold, or just not good. And then for the next one, it's infiltration and how to calculate. For infiltration, it refers to like whenever the air that leaks into buildings, which are caused by construction quantity, wind pressure, and the difference in temperature. Whenever I think of infiltration, I kind of think about how a lot of the sliding doors that a lot of um, stores have, how they're the sliding doors that are automatic. A lot of the times, it's like how the air, how the air from the outside is able to come inside, and then that'll like change constantly. There's always a change in fresh air and everything. And a lot of residential homes and small buildings rely mainly on infiltration in order to bring fresh air into the area. And another thing to note is that one air change per hour means that the air within the building is replaced by the outdoor air every hour. And air rate change is in CFMs. And then there is the formula for it. And then, so for each, so OA stands for outdoor air, then volume stands for volume in cubic feet. ACH stands for rate of air change per room. And for an example, let's say that there's a room that's 13 by 17 by 10, and the air changes at a rate of 4 point per hour. Then you plug each of the variables into the formula. So for example, you multiply the area of the room by the air change of rate, and then you divide it by 60. And 60 just represents the 60 minutes of an hour. Ventilation, so that means that the air that's brought in through fans or vents or anything like that, that also keeps the area odor free. And usually ventilation goes hand in hand with occupants and their activities. To calculate ventilation, you simply have to multiply by the estimated TFM by the number of occupants. So let's say there's like a classroom that can hold about 50 students and teachers, and the estimated CFM is 10. So then all you do is divide and divide. You multiply 10 by 50, which equals 50 CFM year round. And then for estimating heat loss. So in order to estimate heat loss, we had to find where the highest peaks of the building that cause the heat loss to happen, and then that's how we used to find the rest. We also have to know what kind of conditions the project is in, which refers to the temperature. So let's say if it's going to be cold, is it going to be hot? Is it going to be humid? Is it going to be rainy? All of that kind of helps figure out what we need to do for the project. Another thing is knowing the quantities. So for project quantities, the examples are like outdoor air, glass, lighting, people, ceiling, roof, walls, floors, and slab edge. And I made like a little note for each one, but for outdoor air, you need to use infiltration or ventilation to find it. Glass, you only need to know the glass area to find it. For lighting, you have to calculate without lighting so that you find the perfect heat capacity. And then people, we need to calculate without people in mind. And then ceiling, roof, walls, if you have any areas, find the average U value. Then for floor and slab edge, I didn't really have anything for it, but for floor, it really depends on what type of material you're going to be using for the floor. Same goes for the slab edge. Excuse me. So calculating heat gain. Heat gain is calculated through two formulas. One is used for solar heat gain through glass, which for it is so it's Q solar equals SM times A times TD. And SM stands for the factor in BTUS per square feet. A represents the glass area in square feet. CS stands for the shading coefficient, which is the percent of solar energy through the glass. And so Q solar is the rate of heat flow in BTU per hour. But we use this mainly whenever we have a lot of windows, because windows do tend to gain a lot of heat due to the sun that's always hitting on them. So we have to figure out how to find that. And the next up would be the heat gain through roof and walls. And this is a formula. This formula we use to find, through the roof or walls, because the roof and walls are always constantly being hit by the sun. So Q conducted 2 equals U times A times ETD. U stands for the conductance value of the roof, or the U value. And then A is the area of the roof or wall. Then ETD means the equivalent temperature difference that allows heat gain for both the air temperature and the solar effect. Then Q conducted 2 is just the rate of heat flow in BTU per hour. This also helps you find the heat gain for opaque roofs and walls. And that is it. And a lot of this I got from our book, which is, I swear, is very helpful in a lot of different ways. But thank you for watching my presentation, and I hope this was helpful.